there are
Yeah.
five people waiting, so
Good.
okay.
That's good. That's good.
Yeah,
It's
that's nice.
probably all my family.
And probably our people from Australia and Tasmania that like to be here.
Oh, that's
So,
cool.
so
That's really
I'll let Tanya make sure I put it on. I hit start streaming. This is the informal part of this, right? It's like, did I
Sure.
actually start this?
That's funny.
We
That's
ran
funny.
into that last week. I thought I hit the
Mhm.
button and I didn't. And I started talking, and they're like, "No, we can't see you, can't hear you."
Oh, that's funny. Yeah, you
Yeah,
gotta.
we are definitely live.
Okay,
Okay,
cool.
good.
Awesome.
We're live. Yay.
That's wonderful.
Yeah. Yay. So
Yeah.
anyway. Oh, go ahead.
No, I was gonna say you have to verify with the audience that all the audio is working
Yes.
properly
We
and
got
all. Yeah.
video. We got
Yeah.
audio. I
hmm
hit the right button.
I jumped into YouTube for a little bit just to try it, and I have to say I really respect all the people that do YouTube like
I
full
do.
time, right?
Yeah.
As a career, and even the people that are just making videos once or twice a month.
It's a lot
I
of work.
mean, it is a
It's a
lot of
lot of
work
work.
that, yeah,
Like
every
and then like this, I use OBS, this like free
Oh, that's so
broadcasting
funny.
thing.
Yeah, yeah, yeah. Yeah, I'm familiar
So
with that.
every once in a while, this is where I get mixed up. Like I'll hit the wrong button or share the wrong screen or something because it's like,
Sure. Yeah, so that's complicated software. That's the good stuff.
yeah. I mean, it
Yeah.
does some cool things, and I haven't even
Yeah,
really
yeah.
gotten that far into it, but
Hmm.
eventually I'll get there.
Hmm.
So anyway, I should probably introduce you since we just started
Sure.
chit chatting. So welcome everybody in to Space Weather Unplugged. We have our guest speaker today, Chris. He's with the M2M office, and he's a professional space weather forecaster. You know, unlike all of us that are more amateurish. But so we always like to talk to our professionals because this is where we get our information from, and um, so it's always fun to have them on. And we respect the heck out of you, and
Thank you.
because we know it's not easy, just from watching it. You know, because you have to create forecasts from really not a lot of information. I mean, compared to like terrestrial weather that has a lot of information they can draw from, we have not much. So we
Yeah.
respect the
Thank
heck
you.
out of
Thank
it.
you so much for the invitation. I'm so excited to be here. Yeah, I have a weather background as well, so I definitely know what you mean by the lack of data in the space weather world. That
Yeah,
is absolutely true. But yeah, I'm very grateful to be here, and thanks to everybody that's tuning in
yeah.
online as well.
Tune in, and then if you and like always, if you have any questions, just put them in the chat. We'll get to them. But I guess we'll just start with well, I'll start with what I asked you prior to streaming. Is like, so how long have you
Sure.
been with M2M? You know, if you want to do a little bit of background, because
Yeah.
now I'm
Sure.
intrigued because you talked about your weather background.
Yeah, yeah.
So
Yeah. I try to give folks the 60-second summary. So I
yeah,
do have a my bachelor's is in meteorology. I went to school on Long Island, Stony Brook University for my bachelor's. I knew I didn't want to do kind of like I don't know, National Weather Service type work,
hmm,
or I don't know, kind of television meteorology. I wanted to do something kind of analytical and more like math-based, model-based, that kind of a thing.
okay,
So I knew that was kind of always, present. And then, yeah, Goddard, I think in 2017, they kind of had like a summer boot camp where you could just kind of walk in and learn about space weather. So that's kind of how I got my bearings in space weather. And I was like, attended this 2-week, 3-week program led by the scientists. And I think they're trying to actually get that kind of spun back up eventually. I know with COVID, it kind of got, um, you know, the yearly cycle of having that kind of boot camp thing,
yeah,
kind of got disrupted. But yeah, and so in 2018, I attended that camp, and that kind of gave me my bearings. And then I supported the Department of Defense for a little bit with some of my colleagues that might potentially be watching this right now.
good,
So yeah, there's a space weather office out in Nebraska and at Offutt Air Force Base, and then I moved to here, and I've been here since late 2021. I've been with NASA. I took like a very short leave of absence for a couple of months, but yeah, generally since late 2021, I've been kind of supporting. Well, since 2018, I've been doing
okay.
space weather. Like so, yeah.
That's awesome. I have found that it's at least in the classes that I'm in with the SWIN program, there's a lot of meteorologists in there, and it's like they seem to do it as an elective, and then they're like, this is really cool, and then they end up doing the space weather thing instead. So it's really fascinating.
It is interesting. A lot. Well, I mean, some of the physics is definitely the same. At
Yeah.
least the intro level physics. Some of the, even like, I was learning that like some of the equations for like gravity and that kind of a thing on
Hmm.
stars are, also used in meteorology as well.
Okay.
Like, I don't know. So there's a lot of there is a lot of overlap, I think. Even though I guess like if you talk to space weather people, you're like, nah, there's not really a ton of like, yeah, from the operational side, there
Yeah.
doesn't seem like there's a ton of overlap between meteorology and space weather, but yeah, I know it is interesting that I have a whole bunch of friends that have a meteorology background too that
Yeah.
do space weather,
So
so
it seems like it's
yeah.
just kind of, and I know now they're at least with like with Tamitha, and with this program, with the SWIN program, it's like it she's been her and a couple of have been trying to get these different fields to talk to each other too
Yeah.
because everything's treated as like layers with like
Mm-hmm.
a hard boundary, and that's not the
Right.
case.
Yeah.
So now it's been kind of nice to have this overlap because we've been finding out that space weather does in fact impact some of the terrestrial stuff too, which was often just
Yep.
no, that
Yep.
doesn't happen.
Yeah, yeah, it's gonna take a like a groundbreaking theory to kind of tie them all together. But
Yeah,
Tanya and I, we were just talking about this a few minutes ago before the stream started
yeah.
that, there are pilots that, would like to know about solar energetic particle events, and yeah,
Mm.
there is more overlap. And then the whole sprites thing as well.
Oh yeah,
Yeah, just that like the interaction at the upper atmosphere with space weather and like thunderstorms and stuff too.
yeah.
So
Because I don't think I've ever actually looked into what sprites are, or do they know what they are yet?
I'm definitely not
Okay,
the right person to talk to. Yeah, some sort of like discharge like process or something. Like
okay.
that's so like it occurs on such small time scales that like we didn't really know about it for a long time, I guess. But
Well, now
yeah,
now
I
I
don't
got
know.
something else to read. I'll
So
look
do
up
I.
because I was like,
So
huh.
do I.
Yes, I do know that they're way up high because
Yeah,
like I
yeah.
know the people that photograph them. Like you have to be, they're usually like 100 or 200 miles away from the storm, and that's
Oh
how you
wow.
can actually see them. So they're definitely way up high.
Yeah. Yeah, that is cool. Yeah, we're learning things like and like advent of cameras and that
Mm-hmm.
kind of technology too. Like I think there's and you all could speak to this better than me, right? There's probably some changes to how we think about where the aurora can be seen,
Uh huh.
right? With the advent of cameras, right? Because
Yes.
like yeah, like back in the day, I'm sure you could only see it here with the naked eye, and now it's like,
Yeah.
we're seeing them more frequently at southern latitudes, but
Right. It's
yeah.
funny because me and Tanya were talking about this too, just before this, because
Okay.
we were like, it seems like we need to come up with a framework of what's technical aurora and
Yeah.
versus like actual visual aurora, because in a lot of these groups, like for example, like last night, there was a isolated kind of substorm that happened,
Mhm.
but and then it was like, oh, it's out statewide in Michigan, but not really. Like it's all subvisual, but the
Yeah.
camera can pick it up.
Hmm. Hmm.
So it's like, do we want to push that? Because it's not like you can see it, and I
Hmm.
think that's kind of an interesting
Yeah.
point where we're at in this community anyway, because it's like everybody wants to be all excited about it, like, hey, the aurora's out, but then people are like, well, I can't see it, so then they get mad about it.
But
um
but the processes are still happening.
yeah, so it's
Yeah.
like, it's so yeah, to that point, long-winded story. Yeah, cameras have changed what definition of where aurora can be seen by
Mm,
far.
that's funny. Yeah.
So I guess we can segue into,
Yeah,
so
sure.
what is like your day working you know, at M2M? Like,
Yeah, the operational side is
mhm.
it's or maybe pseudo operational might be the right term. Yeah, it is generally I think we're starting to like create more of a process that's a little bit more um I don't want to say stringent, that's probably not the right word. Just a little bit more focused in terms of procedures that were kind of repeating the same kind of procedures.
Hmm.
So like the team was kind of previously spun out of more of a research group.
Okay.
So things were a little bit looser to begin with in terms of um, sort of our activities day
Hmm.
to day. But right now, we analyze the sun. We are kind of responsible for populating Donkey, which for folks online, that is essentially like it's a database, a space weather database
Hmm.
of different phenomena. I have a couple screenshots in my that to show
Oh
people
yeah, actually,
to eventually to get get
let me do
folks.
that, and then so that way when you get there, you can just share.
Oh, cool. Okay, awesome. That's good. So yeah, it's kind of the day to day right now is like populating Donkey. We send alerts and notifications for NASA organizations and missions that could potentially be affected by space weather. Um, it is a lot of kind of thumbing through the imagery and the
Hmm.
satellite data that we do have available, of course. And then we do like this talk tonight will just be kind of focused on the modeling aspect.
Right, right.
We have the CME modeling aspect that we're kind of launching these simulations of solar storms, which you all know about, of course, and then the solar energetic particle modeling
Hmm.
piece as well. So um, we kind of look at a broad number of like solar energetic particle models to help support the ISS folks
Right.
through. So yeah, so we support Space Radiation Analysis Group at Johnson.
Hmm.
So we're kind of keeping our eye on all these solar energetic particle models to kind of see if they're hinting at something, some big event to occur. Um, like for essentially for protection, if the astronauts in the ISS would need to like go into some sort of
Yeah,
um, shielding or protected room or something. So
that's cool. Yeah, I do
yeah.
know after learning more about space weather and specifically radiation events, I'm like, you won't catch me in space anytime. Even
I
if
think
even if somebody gave me a free ticket up there, I'm like, I'm good. I'll just look up.
it's it's happening now, right? Like we
Yeah.
have we have just I don't know, quote unquote regular people,
Uh
right?
huh.
Going to space.
Yep.
So it's definitely happening. I would not make the ride. I'm too nervous about heights to
Yeah,
like
I couldn't do
I
it.
I couldn't do it. Yeah.
Now
Once
it.
I'm there, if I could teleport and I was just there, I
Yeah.
could that would be fine. I would handle it fine.
Maybe
But
there for like a minute or two, come back.
yeah.
Now, are you guys support like? Do you find or think that you guys will end up supporting some of these private entities too that are doing the space tourism stuff, or is that kind of too early to tell?
Yeah, the great question.
Yeah.
We've had actually some conversations with the folks at SpaceX, even Blue Origin,
Okay.
as they begin to kind of create their own, space weather teams that are actually going to be watching. We've obviously we had a couple of really big launches, right? That
Yeah.
particularly the 2022 one, where SpaceX, for the folks that are not aware of this, SpaceX launches 40 or something approximately satellites to low Earth orbit. We have a geomagnetic storm, and then like I don't know, a 70 or something percent, 60% of them all like fall out of the sky.
Yeah.
Um, so so like yeah, as a result of that, I mean, I think the private companies are starting to think about this a lot more seriously.
Okay.
And yeah, we've had some conversations with folks about how we can best support them, but yeah, our day to day is certainly more focused on NASA, I would
Okay.
say.
That's cool.
Um,
Um,
yeah.
I'm glad that they are thinking about it. So that a step one. Because I'm like, if you're gonna
Yeah.
send random people up to space, it'd be nice to have a a handle on what you're launching them into.
Yes. Yep. And there's launches that, SpaceX is launching pretty frequently and
They
regularly.
are.
So,
Yeah.
I know that there's been more formalized processes, more on the NOAA side, I would think, in
Yeah.
terms of like where to find the data where to find the space weather data, where to find the right forecast for what they need.
Okay.
But yeah, yeah.
Sweet. Well, I know
Hmm.
that was an interesting little segue, but
Hmm.
it's kind of recent news because
Yeah,
we all know what happened. Like, what was it, 2 weeks ago now? When
about 2 weeks.
the uh the celebrities that went up to space that caused a stir on the internet. So it's like oh yes, space tourism. This is a thing.
Yeah, yeah. It's a very interesting time that we live in right now,
It
honestly.
really is.
Yeah. I don't know
It,
who was doing the space weather forecast for them, but
yeah.
it was not us.
So now it's like it's fresh in everybody's head. So figured
Yes.
I'd touch on it. So I guess if you want to roll into like
Sure,
the
sure.
forecasting aspect of it, we can head
Yeah.
down that
Y-
avenue.
Yeah. Do I need to share my screen at all?
I would, just the way I have
Okay.
this like broadcasting
Yeah.
here.
Yeah, I kind of have something, a little on the formaler side.
Okay.
Tanya had asked me essentially to do something on WSA Enlil.
Oh yes,
Um,
yes.
you could cut me off at any point. It doesn't need to be, yeah. So it could be more of a conversation, or if you have any like specific questions or
All
anything.
right.
But
Well,
yeah.
we'll start there, and then if questions come up, I'll
Sh-
holler, or
Okay,
if there's
that's
any in the
perfect.
chat.
That's perfect. That works perfectly. Okay. Hopefully,
Yeah, hopefully it works. I think yeah, there we go. I see it.
yeah. Should
Yeah,
theoretically
because I know I'm like I gave you all sharing power, so
work. Okay, so hopefully you should see my
yep,
title screen.
I can see it.
Awesome. Technology, isn't it lovely when it
Oh
works?
yeah,
It's good. It's
absolutely.
beautiful. Okay, so yeah, Tanya had wanted me to talk about WSA Enlil, and so this is essentially is a model for the solar wind that is streaming out for the sun. And then of course there is that's kind of what we would refer to as the ambient model,
Mm-hmm.
um, kind of the background solar, steady state kind of a thing. And
Okay.
then we can insert coronal mass ejections, or solar storms essentially into the model, to see how the CME will sort of interplay with the solar wind. So that's what this model is. And those are pictures of what it looks like from different entities on top there. The left side is what it looks like from NOAA,
Okay.
and the right side, of course, is NASA. And I know I'm going to speak kind of broadly because I know online we probably have a pretty broad audience of folks that
Yeah.
that watch this stuff very closely, and then people that don't really have the solar physics and the space weather background as much. So I'll try and keep it kind of, you know, but I know some of you folks definitely know that already.
Yeah.
Um, so what we're talking about is in space weather forecasting, solar wind prediction, CMEs, solar flares, and solar energetic particles. So that's just, that's just the space weather forecasting as a whole. Kind of analogous, as we talked about, to weather forecasting, but using data from generally either close to the sun or around Earth's orbit. So CMEs in particular or solar storms essentially. They're these massive ejections of solar plasma and magnetic field, and they are observable in coronagraph instruments, of course, which it's a telescope that essentially blocks out the stray light from the sun. I know you folks know this already, but just for the folks online that may not know what we're looking at here in the coming images, we block out the sun's bright light to be able to see these big solar storms.
Yeah. No
So
worries. It's always good to
yeah,
reiterate things.
yeah,
So.
yeah, just to give kind of a ground level here.
Yep.
Yeah. So this talk is going to talk about this model in particular. It's really used for the solar wind and really for CMEs, as you'll see. And then we'll talk about just some of the benefits of it, limitations, and then how it's actually used kind of in operations.
Fantastic.
So, um, so this is kind of like two models that are put together. Hence the hyphen there. We have Wang, Shili, RG. So you can think of it kind of like models that are, one is essentially much closer to the sun, and the other is a little bit farther out, sort of into the heliosphere.
Okay.
And so the WSA portion of it uses solar magnetic field maps. So we're mapping the sun and finding essentially where the intense magnetic fields are. And essentially, the modeling gets us the solar wind speed at a very specific distance away from the sun, 21 and a half solar radii. This is in operations, a very important boundary.
Hmm.
And it kind of distinctly separates these two different domains that we have. So the coronal domain, where, you're much closer into the sun, you have forces that are a bit different than out in the heliosphere. And then past 21 and a half solar radii, you have the heliospheric domain.
Okay.
So yeah, the solar magnetic field kind of strongly influences the solar winds, like closer into the sun than this distance. And then after this distance, the solar wind kind of is radial, meaning that, it travels in essentially straight lines. And it's more fluid, like the behavior of the solar wind is a bit more fluid like. So that's sort of the inner portion of the model. And then the outer portion is actually kind of simulating the heliospheric conditions. So like sort of beyond 21 and a half solar radii. So Enlil is a three-dimensional MHD model. MHD stands for magnetohydrodynamic.
Hmm.
And so yeah, this is a model that when coupled together with WSA allows you to kind of, and I'll show a picture of it in just a second. I'm going to talk about kind of the inputs and outputs before we actually get to what it looks like. But
That's
so
cool.
these are two. Yeah, yeah. So
I always
these,
actually wondered what WSA meant for or stood for, so now I know.
yeah. Those are the folks that built it. And Nick
Yeah.
RG in particular, he is at Goddard. He's really, really wonderful person to
Awesome.
talk to. Yeah, I've got to every now and then he'll give a lecture kind of in the building that we work in. So feel very privileged to be able to work in the building with him.
That's awesome.
Yeah. So these are let me see if I got a little screen in the way, so okay. Just moving screens out of the way, sorry.
Oh, you're good.
So inputs and outputs for this. So the input to this WSA model is essentially it's a magnetic field map. And I'm going to show exactly what it looks like in just a second. It's a map of the sun that shows where the really intense magnetic fields are, and then time essentially. So what the Carrington rotation number is, or essentially some understanding of what time is currently.
Hmm.
The magnetograms come from GONG, the GONG Observing Network, and HMI, which is the Solar Dynamics Observatory. So SDO is a NASA satellite, and the HMI is the instrument that allows us to get these magnetic field maps. And so that's kind of the input to WSA, and then the output is actually getting the velocity, the wind speed, at this very important boundary, so to speak.
Okay.
The Enlil portion takes that speed at that boundary. So that's kind of like it's like if you're making a pizza, right? And you're like halfway done with the pizza, now you got to put the pizza in the oven. So weird metaphor, but so you're taking the wind speed, right, at this particular boundary, and you're plugging it now into Enlil. And so there is essentially a whole bunch of equations, the really nasty MHD that I did not go to school for. There are some folks online that could probably speak to some of these really nasty physics equations that require calculus to be able to solve those equations. That's what the modelers do, way above my pay grade. So yeah, equations for plasma mass, momentum, and energy density. And so really, essentially, some really hardcore physics where you have magnetic fields and electric fields and then transporting that, through time. And so that's the input. The output is what we're interested in here. We're going to look at a lot of the output today.
Fantastic.
It's the good stuff that everyone gets really excited about when they see something on Twitter, right, or Facebook. Yep. They go, "Oh, the CME is going to hit," right? That's essentially what the output is. So it's a time series that has velocity, density, temperature, and it doesn't necessarily have to be at Earth, right? This could be anywhere in the heliosphere. The Moon to Mars office at NASA, right? Mm-hmm. We support other missions, and so we're able to get those we're able to get those things of interest, velocity, density, temperature, all these things at other missions too. So it's primarily used for Earth, but we have the capability to like look at other locations and, oh, is this CME going to hit Mars, so to speak?
Okay.
Which down the line could be pretty, that could be important, of course,
Oh,
when
yeah.
yeah, we'll see. We'll see as far as the Artemis mission and stuff. So that's eventually the goal is to get boots on Mars.
Right.
So yeah. This is what the magnetogram looks like it's from WSA Gong. So all these really bright regions and dark regions, those are essentially active regions that are or sunspots that are responsible for creating, so this kind of a thing, this background would sort of get plugged into WSA Enlil, essentially.
Okay.
Okay. So this is before we even talk about like a CME or putting a CME even into this model, this is an example of kind of the ambient version. So we haven't put a CME in there yet. This is just kind of what's happening. This model could be running just constantly, and in some cases it is running constantly. At SWPC, it's running just constantly, and you can see what it looks like on any given day. This was from just a couple days ago, actually, and we're going to talk about kind of how to look at this model. This is a very complex model that obviously has a lot of colors, probably referred to as the pinwheel diagram or something like that. Yeah. There's kind of a lot going on here if you're sort of unfamiliar with it. So I'm going to kind of take you through all the different slices. This portion of Enlil is so let me back up even further. The model is so complex that we have to basically, break up the actual output and slice it in order to be able to understand it properly. So there's large volumes of like 3D solar wind data, and in order to be able to we could have a three-dimensional model, and in some cases that exists. But for analysis, using it for as a tool for analysis of is this CME going to hit this location, we have these different sort of cuts they're referred to as. So there's slices. This red box here, and I color coded it, so hopefully you'll be able to match here. So
yeah.
The left box is the ecliptic plane. It is a slice basically along the plane of Earth's orbit around the sun. And that's where a lot of planets and spacecraft usually reside. And it's a top-down view of the sun-centered solar system. So in this picture here, of course, the yellow circle is the Earth. And then this white circle, you might think is the sun. It's actually the 21.5 solar radius boundary. So the sun is kind of like inside of that white circle, but it's actually kind of even bigger than the sun slightly. And so the middle panel here is the meridional cut. It's kind of as if you were cutting along the Earth-Sun line and looking at it from the side. So it's a vertical slice through the sun's poles and equator at the solar central meridian. And so with this one, you can actually see things that are happening above Earth's orbit and below Earth's orbit. And I'll get to the darkly shaded pink in just a second. And then the right-hand side is called the azimuthal cut. And so that is a slice at very constant radial distance away from the sun. And so this particular one you see at the top there, it says R equals 1.0 AU. That's because this cut is at 1 astronomical unit away from the sun. And that is where the Earth is.
Okay.
And so this one is used for analyzing structures at a very specific kind of distance. And so I'll back up and remove that for a second so you can see the reason, right, for this big can you see? Yeah, you can see my mouse probably,
Yep.
right? Awesome.
Yep,
okay.
can.
So yeah, so this is that's good. That's definitely good
Yeah,
because I wanted to point stuff out. Yeah.
Yeah.
So yeah, this darkly shaded pink, right, is related to structures on the sun here. This is a coronal hole for folks that are not as familiar with kind of solar physics here. This is an area on the sun with open magnetic field lines where the solar wind is streaming out very, very quickly. And so this is kind of, you can see based on this model, or the model is suggesting that Earth can, potentially be sort of clipped by the northernmost kind of portion of this coronal hole, but most of the really intense solar wind speed is actually below Earth's orbit, like literally underneath the Earth. So, and so this is kind of what the model looks like just before we even put a solar storm into it. It does have the capability to kind of model coronal holes and other kind of structures like that. And if there's specific questions about this too, I'm happy to go back.
Yeah, I'm trying to monitor a little bit, but yeah, Tanya's been grabbing some of them. But I think we're good right now.
Okay, lovely. Yeah,
Yeah.
I could also go back at the end too
Yeah.
as well. Yeah. Okay. Um, so that is kind of the general overview of the um kind of the ambient solar wind. And now we have kind of an overview of the cone model, which is essentially the CME included into that model. So after the background solar wind map is produced, you can basically overlay solar storms on top of this ambient simulation to see if there's any interactions between the solar wind and the CMEs. And for the really strong CMEs, the really powerful solar storms, oftentimes the background solar wind doesn't really play in as much of a factor. But when you have a big structure like what we just saw with that big coronal hole,
Hmm.
it absolutely could. There could be deflection if you have a really kind of weaker CME. There could be some interesting complex kind of interactions that go on. Um, so yeah, we need to, in order to be able to launch this, there are some parameters that we need. And so we measure the CME using software or tools. Uh, the one that we use at M2M most
Hmm.
frequently is called SwipsyCat, which was developed, of course, at NOAA. And so these tools give us some of the parameters that we need to be able to put the CME or put the solar storm and insert it into the model. So we have here velocity, angular width, and the latitude and longitude on the sun where essentially it originated from. And that in itself is um, can be difficult because these storms or filament eruptions, there are these interesting things that may not essentially originate at one sort of point.
Right.
And so that's kind of an uncertainty with measuring and also with these models is it's kind of a limitation. Um, it assumes as though you're kind of like launching the storm from one sort of specific point from the sun. So, um, yeah, and then the last thing here is so the CMEs are treated as like these simple expansions, constant speed, and then propagating through the ambient wind field.
Alrighty.
Um, for folks that are inclined to read papers, oops,
Not
my
Tanya.
apologies.
I always
I've
have to
I've
jab at
spoken to
her.
her and I know she will read this paper. Absolutely. There's a paper in 2003 that might be of interest to you if this is your forte. So here is an example of what the model now looks like with the CME sort of input into it.
Hmm.
Um, so this is an example from a couple days. So this is like mid-April. It's about a couple weeks ago. There was kind of just a faint kind of minor CME here seen to the east. The right hand, for the folks that have never seen this image before, this
Hmm.
is one of the coronagraphs where the white circle is the sun, and we're blocking out essentially the solar atmosphere in order to be able to see kind of the tenuous outer atmosphere of the sun here. So a solar storm was kind of observed in this direction, and essentially upon inserting it into the model, this animation kind of shows the direction of the CME. Um, and so not much for Earth for this one. This is one where it would have missed Earth, the
Yeah.
yellow circle here, but it was predicted to actually impact Osiris Apex, which um, is interesting. So one of the things that we do is kind of alert other you know principal investigators of other missions and stuff about the potential whereabouts of some of these CMEs.
Makes sense.
Yeah.
Yeah, that's like a direct hit for that poor little thing.
Yep, pretty much, yeah. This is even more. This graph here shows you like how strong of an impact it was.
Yeah.
These are some of the outputs, right, from like the numerical outputs of what the what the model is producing. So you have here magnetic field is this black line here, and you can see beforehand we were probably sitting around 23 nanotesla. That's the magnetic field strength, and then of course this big rise here is the arrival of the CME. So this is absolutely a really good tool for indicating when these solar storms are going to arrive at Earth. And thankfully, a lot of it is actually easy on our part at NASA because we have algorithms that are built in place, right? Where the computer is actually smart enough to say, oh, yep, here it is. Here's the arrival. It's right at this exact time. It's like the 16th of April at 2100, right? So like almost like no thinking required, which is kind of nice. But that's not always the case.
Right.
Some of the weak, faint ones, we have to really analyze it very closely, and kind of manually look at it. Yeah, I think that's all I want to say. There's some other parameters that are used as well, ion density and velocity, that you can sort of obtain from this model.
I'll ask this question since it's kind of pertaining to this. So Vincent, he asked, in the pipeline from CME happens to the Enlil model, how much manual input is required from the space weather forecaster, or is any of it automated?
So yeah, great question. Hi, Vince. So there is a good amount from the CME. So I'll start kind of the measurement process. The measurement process is completely manual. So how that works is you are looking at the extreme ultraviolet imagery of the sun, and this right-hand image here is an example of that. So you're looking very carefully on the sun for a particular source location of where that eruption took place, and then you are using that kind of as essentially your cheat sheet to take a best measurement of it. And by measurement, we say that we are trying to obtain the velocity of the solar storm, the time that it is going to pass by this 21.5 solar radii time, and then also how wide it is as well. So that whole process is manual.
Okay.
And then the actual launching of the simulation too, that essentially is that's a bit on the manual side as well. So we're taking that information and plugging it into essentially an environment that is running the model with that information. So
okay,
yeah, hopefully that helped to answer the question. But
I'm sure if there's any follow-ups, he'll put it in there.
Yeah, a lot of the what's nice is a lot of the graphics are produced it's a very robust kind of environment where all of these beautiful graphics are sort of produced without a lot of effort on our part, kind of a thing.
Okay.
So
yeah.
It's a pipeline that's been already sort of built where we plug in the input and then the output is kind of given to us within a certain amount of time. But and I am going to talk actually right now about sort of the applications of this in the operational, at least some that I can speak to, more probably on the NASA side. So this model is like used internationally. This is not like a NASA model, right? It is used internationally by different agencies that are monitoring space weather, and it's not necessarily the only way to determine CME arrival times, but it is a good one that is used frequently, and it's kind of the leading model really right now for NOAA and NASA. Primarily, I would say. The outputs, of course, we talked a little bit about this already. The outputs include the CME arrival time, the solar wind conditions at Earth. One thing we didn't talk about is kind of the estimated geomagnetic activity. So we'll talk in the next slide very briefly about that. But for Earth having a magnetic field, the output of this model is given to us in a way where we can estimate the geomagnetic activity at Earth. So for the folks that, maybe haven't studied space weather, this solar storm launching from the sun is going to interact with Earth's magnetic field. And then there are really complex magnetic field, essentially enhancements that occur at Earth's magnetic field. And those processes can cause the aurora to be enhanced and for, geomagnetic conditions to increase. So there's kind of another domino for CMEs that are occurring at Earth is to potentially try and predict what the KP index is. So it's a number. You all know this very much, but a number from 0 to 9 to essentially try and indicate how geomagnetically active we are.
And then while I have you here, so it's not. I mean, none of these. We're like no questions basic. He's like, I'm sorry, it's a basic question, but it's a variable question. So I just
I'll
see what.
No silly questions.
Yeah. How far in advance can you forecast these out? So, and I know that's kind of variable because depending on like coronal holes or how aggressive a CME is, things like that. So if you want to speak to that.
Yeah. Great question. Very, very good question. It is a function of, two major things. One is the CME speed. So we have a lot, a faster CME is going to potentially arrive at Earth faster. So we have a lot less time to work with. And I'll caveat that by saying most CMEs are going to arrive at Earth between about 2 and 3 days. There are some very, very fast ones that could be on the order of 24 hours, and there are historical ones, right, that have been like 18 hours or right, even
Real
so
fast.
really fast, where like we would be, calling up, I don't know, we'd be calling up the whole chain, right, saying like
yeah.
So on average, we have some time to deal with these things. The other thing to consider is like the data availability. So we have this right-hand image here of this telescope. Sometimes we just don't get data from it, and the reason is the main reason is that this right-handmost instrument is actually not operational. So it was developed for research purposes. And we get data pretty frequently from it, but it's not a sustained 24/7 type data feed, essentially. And so there have been times where we would have to actually wait several hours. We see that the CME maybe has occurred, coronal mass ejection has occurred, but we have to wait like 4 to 6 hours or something in order to wait for the imagery to be downlinked properly to Earth. So so the short answer is yes. There's a variable amount of lead time for each one of these events, kind of depending on its particular circumstances.
Perfect, thank you.
Yeah. This is a picture of the ambient run from NOAA SWIPSI, and I have the link here. We could I don't know if we can make these slides available, but in any case, NOAA on their website does have this link for you to be able to actually look at this image, and the website is constantly being updated with the kind of the latest WSA NLO run. This particular one that I grabbed is kind of an ambient run, so it doesn't have any CMEs added into it, but occasionally when there is a significant CME, of course, this page will reflect that. So, and then kind of transitioning more to the NASA side. So there is a tool here. I'll show a picture. It's a website referred to as the CME scoreboard. And so this was developed at NASA by the Community Coordinated Modeling Center. And it's essentially an aggregation of the whole international space weather community's predictions of CME arrivals specifically for Earth. So that could mean the WSA NLIL plus cone model, but it may also be other models that are used to possibly predict, an arrival at Earth. So it's, there could potentially be other sort of techniques that are used as well. And I'll show a picture just in half a second with yeah. Um, and kind of once these arrivals occur at Earth, there's kind of a process to kind of get them validated. We have at NASA Goddard, we have solar wind scientists that are actually reviewing the signature that plays out in the solar wind, that can help us diagnose, okay, well, clearly there was a CME arrival here, but maybe there were 2 or 3 CMEs that were sort of mixed in, and that happens occasionally sometimes, where there's more complex signatures. This is the picture. Very overwhelming if you've never seen this before.
Right.
Yeah, it can be very overwhelming. This is just one particular CME entry from the scoreboard. And this is kind of notable here because it normally doesn't look this busy. This was an event where you can see just by the number of boxes in the bottom here, like a lot of eyes from the international community were looking at this particular event. And so what you're looking at are predictions from the entire space weather community, the international community, on when the solar storm or CME would be predicted to arrive at Earth. So that's the left-hand most column there, predicted shock arrival time. There's also an ability to try and predict the geomagnetic storm strength as well, which is kind of in the middle row there, that max KP range, and then different methods, different models that are used to make this prediction. And so, yeah, this is a potential CME from, it's actually, let's see. Yeah, this was the CME from this past month that actually did give us a pretty strong geomagnetic storm. I don't think you'll have to refresh my memory. I don't think we saw much of this though, because the timing.
Yeah, it was
timing
during our daytime. At least in North America, it was entirely daytime.
Yeah. So this was this was just an unfortunate event for North America, I think. But yeah.
But that was the weird one too, because that was like that weird filament that was like in 3 different pieces or something. Because you talked about filaments being difficult.
Exactly. It's actually the bottom right here. That's the picture of this filament, and I'll show kind of what the model looks like for this particular filament, and the solar wind that kind of developed. But real fast strengths for the model. So it goes through the whole heliosphere, goes from the sun all the way out, to like 5.5 AU astronomical units. So that's as far as like past the asteroid belt, all the way out at Jupiter. So we can predict CME arrivals like all the way out there, which is great. The model's relatively fast to run. It's about 2 hours. Last I heard, definitely not, don't hold me to this. Last I heard, I think it was about 2 hours for NOAA to be able to run a CME model. And it is about 30, maybe just under 30 minutes for NASA's team to run their model. And so the KP index, that bottom hand, or the bottom bullet there, talks to the KP index being able to be sort of forecast from this, based on a clock angle concept. So we don't really know the magnetic field orientation of the CME as it arrives, and the magnetic field orientation is very critical in determining if we're going to have a geomagnetic storm. And that's because the magnetic field kind of right at noon in terms of Earth, so the side of the Earth that's facing the sun, that magnetic field is generally northward. And so in order for reconnection to happen very strongly, we need a southward sort of oriented magnetic field. And we don't really know kind of what the orientation of these solar storms are going to be as they arrive. Sometimes it works out perfectly and we get maximum sort of reconnection, but that doesn't always happen, of course. So we have KP index ranges, meaning the geomagnetic activity could be this, based on this magnetic field orientation, or it could be this, could be higher if everything works out in terms of the direction of the magnetic fields. So if all things work out, basically. And then uncertainties, the strengths here, like oftentimes we're within about 7 or so hours of, I would say in general, like some CME predictions have uncertainties of up to 24 hours, and but real, I think the community has gotten pretty good in terms of reliably being able to forecast if they do arrive for these bigger events that are recognized as, yep, this is probably going to arrive at Earth. Oftentimes the timing of the event, the predicted time of the event to arrive at Earth and the actual observed time match pretty well, usually within 12 hours or so. There's still there's still this open problem about magnetic field orientation. And so the modeling is kind of like, it kind of neglects some of the complexities of the CME structure and that kind of a thing. We don't really have any say over that, which can be difficult at times. The second one is one that I personally care about quite a lot. I don't know why I care about this so much, but yeah, it's something that I think about quite often. So this is referred to as mass constraints. There's no ability to choose the modeler, like myself or whoever's running this model. We cannot put in the amount of mass into the model, really. And so what does that mean? So theoretically, you could have two CMEs, and they are going to occur at exactly the same spot on the sun, and they are exactly the same velocity, and they are exactly the same, I don't know, half width, and they look almost exactly the same, except that one of them is really dense and it has a lot of mass in it, and the other one is kind of, let's call it hollow. It doesn't really have a lot of structure on the inside of it. And so they're going to be modeled very similarly, and we don't have a way to capture essentially some of the physical processes, like the internal mass of a CME. And another thing is, like, just because the CME looks brighter, right, or larger in the coronagraphs, doesn't necessarily mean that there's more mass associated with it also, which is interesting.
Now, is this done just for model speed run, or is it just because I if I remember correctly, some things are ignored so it can run faster than real time, but
so this is kind of this is like a limitation, is that we don't have the ability to include the amount of mass. And I think if we were able to go in a direction where we could include this much mass, because we're visually observing this to be, we think that there's, going to be a lot of mass associated with it based on its like visual presentation, there potentially could be a benefit to that. It's something that would have to be kind of studied a little bit.
That makes sense.
And I'll give you a great example, or one that I can think of, that a common example that keeps recurring, right? We have these halo CMEs, right? They're storms that are directed pretty much right at Earth. And so in the coronagraph, they appear as these very, 360-degree looking storm, because all, the sort of the blast is coming out in all directions.
Yeah. And
so we know that it's going to hit Earth, and it does hit Earth. The problem is it's really faint. It's really faint. Like we don't think it's like going to be a gigantic big storm, but our modeling doesn't really know how to handle that properly yet. So it could be a very faint but very fast CME that is that doesn't have a lot of mass behind it. And so when we model it, basically what happens is the model kind of overblows the CME and says, oh, Earth is going to get completely, Earth, there's going to be a strong arrival at Earth, right?
Mm-hmm.
But that's not what happens in actuality.
Okay.
So that's definitely a limitation. Is like we don't have a we don't have a volume knob, right? We should have some sort of a volume knob when we put the model in, I think.
Yeah, it's a
Um,
good way to illustrate that.
yeah, there's got to be a volume knob or something.
Yeah.
Yeah. Um, another interesting thing is, um, so we talked a little bit about these photospheric maps um, that are used as input. This
Mm-hmm.
one, right? So basically, these get generated every hour or two. And so what could theoretically happen is, I'll go back to where I was. Theoretically, two organizations, right, they could have the same parameters. So they measured the CME exactly the same. It's at this latitude, this longitude, this velocity, this half width, and they have the same answers. But what happens is one of them might potentially launch the simulation a little bit faster than the other organization. And so what ends up happening is um, they're actually injecting the results, the output, or excuse me, the input. They're injecting it into a different model, really,
Okay.
a different model run of the photospheric field. So um, essentially, the solar data is always changing with time.
Right. Yeah.
So if I launch something at 11 o'clock, it's going to use the 11 o'clock map for the sun, right? And if
Mm-hmm.
I launch the CME at noon, it's going to use the noon map of the sun. So, but if it's the same CME, right,
Yeah.
they're going to be different answers because you're using now it's a pretty small, kind of a small thing, but it kind of adds up in the grand scheme of things.
Right.
Because the data is just constantly being refreshed. Um, so that's that. I mean, it's not necessarily a weakness, but it is a limitation. If you wanted to do a study on a CME from years ago, you would have to go find the solar map data too to accompany it. You
Mm-hmm.
um, can't launch it with today's map of the sun. That's not going to be helpful, right?
Yeah. Yeah.
So the Moon to Mars office in particular, we do not run CME models like after about 2 days or something. Like if it's older than 2 days, we would
Okay.
have to. There's a separate process.
That's
Because
interesting. Yeah.
yeah, the map is no longer good, right?
Yeah.
Yeah, I don't know. It's kind of yeah. It's like it's a roadmap that's gone wrong, right?
Yeah.
Or like it's not everything's now updated. It's like if you're trying to use like the old like Garmin GPSs and you haven't updated your firmware. And
Yeah.
so
Yep.
like there's all these new buildings now and all these new roads that have been built, but you're still in like 2005, you know?
Yeah. That's a good way to put it.
Yeah.
Except that the sun changes all the time, so it's like a little bit
It,
faster.
yes, exactly. Yeah, exactly. Yeah, as the sun is changing, that's like input that's changing, and
Uh-huh.
then you're overlaying that. And that brings me to this last bullet.
All right.
There's so many things going on, right? It's like the sun is changing, and then we're taking measurements, and then, you know, the ambient model could possibly be wrong, or maybe the CME measurement was wrong. Uh, or maybe the CME was like more narrow than we thought. Maybe it was faster. So the troubling thing, the thing that troubles the folks in space weather is that there's not a lot of learning when you mess up or botch a forecast, right? Like you if you're 24 hours off, it's not terrible, but the question is like, okay, well, where did I go wrong?
Right. Yeah.
Did I go wrong, or was it, you know, maybe maybe my measurement was pretty good, and the coronal hole that was modeled was in the wrong place or something.
Mm-hmm.
It could happen, you know, if a coronal hole is expected to arrive at Earth a day earlier or later, and then that's not the reality, it could mess things up. So So there's so many dominoes. It's like sometimes when we don't get a good forecast, we have to like it's hard to analyze. Like, okay, what went wrong? There's so many moving pieces. So, I don't know. Interesting.
It is. It's a bit nightmarish.
A little bit. And this is why I don't want to, this is why like people like me, I don't do model or I don't do any like the complex modeling or anything because um that's a problem for those folks to like kind of have to sort out a little bit.
Right.
Um I can only do what I can, right? In terms
Yeah.
of like measuring something. So, really fast, here is we're getting to like the last couple slides, but
You're good. You're good.
this yeah, this I don't know how much time we have to play with, but this is what you had just talked about, Marybeth. Like
Yeah.
this is this really complex filament eruption um, on the. I'll use my mouse here. So, yeah, this really wide filament eruption here that had all these different lobes they're referred to as, and the extent of this was so you are looking at the sun as though you were from the Earth, and so most of this is going to be we know underneath Earth's orbit
Mm-hmm.
but possibly like how much of it is going to be along the ecliptic plane. So that, the answer to that question is inside of this model here. So this middle panel, um, you can see that a lot of it goes below Earth, but Earth is certainly being impacted by it. And of course, more than one here, really. You can see one, two. You can see there were multiple arrivals in this model. And consequently, that's kind of what ended up happening in terms of the actual solar wind data. So if you've never seen solar wind data before, um, I'll just quickly guide you through what some of these plots are. The top plot, okay, so where this data comes from is about 1 million miles towards the sun. So pretty close to the Earth, relatively speaking, but out in outer space. And this is the solar wind instrument ACE that is essentially used to, determine it's kind of our warning signal, so to speak, that something probably is going to arrive near Earth very
Right.
soon. So it's, 99% of the way to the Earth from the sun. So very close, much closer to the Earth. And the top plot is the magnetic field strength. This orange plot is the density. Purple is the velocity, and green is temperature. And then we have here this bottom plot is, of course, geomagnetic activity, the KP index. So in this particular, model run here, where we see Earth is maybe getting clipped by two of these storms,
Mm-hmm.
you actually see that possibly could have been the case here. This is the plot of the velocity, and you see on April 15th there is one little increase here in the solar wind speed, and then another one that occurs here. And possibly there may have even been a third one potentially. This third one has a density drop. Not much terribly going on with the velocity, but you can see here at this very specific instance, there is a drop in the magnetic field, and these different colored lines are the magnetic fields, essentially the orientation of the magnetic field, the components of the magnetic field. So this could have been maybe two, possibly three different CME arrivals that, we were able to get maybe a 2-day or something notice lead time for this particular event. But the tricky part is trying to figure out the orientation. So this is when the arrival occurred. This was around April 15th. And then the real big storm doesn't actually occur until like midday on April 17th, like 2 days later, right?
Right.
So it's a bit tricky. And this is the southward field that we talked about, of course, that led to that storm, which is great. But I should have overlaid kind of when North America was like in the daylight, because it would have been pretty funny to look at.
Basically, that whole southern part right there.
Yeah, this is right here. Right here is when Earth was in daylight, and right here is when Earth was at nighttime. So we couldn't. It was a lose-lose for us, unfortunately.
Yeah, for us it was. For others, for some other people, they they had some
Yeah.
fun with it, but
We went through that fun event and we
Yeah.
pretty much like looking at the rural electrojet, you can tell when American night was. North America, Western Hemisphere in the night and the daylight. There's quiet for
yeah,
the nighttime.
it's
Really quiet
like
for the
really quiet,
nighttime.
like just crickets, like just.
That's unfortunate.
I don't. It's actually really funny. I
That is
screenshotted it
funny.
and saved it because it's kind of funny.
That is funny. That is really funny. Yeah. It happens, you know.
Yeah, it does.
We're due for it. And that's the tricky thing in terms of like trying to produce a can you see the aurora forecast, right? Like uh when our uncertainties in CME arrivals are 12 hours, I mean,
Yeah.
it's who's to say what side of the Earth is probably going to be better for, looking at the aurora. Like we know as the event kind of unfolds, we're like, yep, this is probably not our night, and
Yeah,
it's the other
yeah.
side's night. But
And we don't have
um,
teleportation devices, so
we
can't just.
unfortunately no, we're not there yet. Unfortunately, yeah,
So.
we're still working on like the speeding bullet trains,
Mhm.
but yeah. Anyway,
So we just cry about it. It's fine.
yep, yeah. Wait for the next one.
Yeah.
Okay, so the last thing here is relating to like running a lot of these models all simultaneously.
Okay,
So this is
cool.
ensemble modeling. And so you're running, so what the purpose of this is essentially to try and gauge the amount of uncertainty in a CME arrival. And so the theory is you have your initial data, you have your initial measurement, that kind of a thing. And then what we're going to do is change the initial conditions just ever so slightly. And then we're going to launch another model, and then we're going to change maybe the velocity a little bit, and we're going to launch the model, and we're going to change the half width just a little bit and run the model. And then we're going to look at the results of all of this. And if all of the results kind of look the same, well, that indicates, okay, well, we changed a lot of things, and yet the results are kind of all the same. So there's good confidence that this is possibly going to happen. Otherwise, there could be a lot of variability in the results, in which case. And so the thing that everyone knows, right, in the meteorological world, of course, is spaghetti plots for
Yep.
hurricanes. And so the right-hand side is kind of what the right-hand side is kind of what plots look like for hurricane paths, right? We're changing the pressure, right, or the location of where the low pressure is by just a little bit. Or we're using a different model that has different physics, right? And so if all of these lines are converging upon North Carolina, well, North Carolina is probably going to get this hurricane. That's not in truth how it works, but there's more confidence, right, that area is more likely to be impacted by a hurricane. And if there's more variability in all of these lines, then of course the confidence is a lot lower. And the joke, right, is the left-hand picture here,
Yeah.
which is like sometimes if you try to predict too far out, yeah.
I like the little heart that's in there. It'd be awesome to see a hurricane move like a heart shape.
I didn't even catch that. That's really funny. Yeah. This is how it feels sometimes.
Yeah.
I would say. Either you're predicting too far in the future, or but anyway. So we do this in the space weather. We do this in the space weather world. Not terribly frequently. I actually did for this event, this filament eruption event. I actually went and did an ensemble just essentially for fun.
Okay, cool.
Just to show you kind of
Yeah.
like what it would look like to run an ensemble for this particular kind of event. And so the process involves measuring the CME like this, using kind of the foot points of where you can actually visually observe the CME. And this is done in a different measuring tool. And doing this like a whole bunch of times, like 50 times or something.
Mm-hmm.
And you can see, I don't know, hopefully you'll be able to see it on the screen here. There's a couple of these little blue circles or green circles.
Okay.
So
yeah.
that's kind of indicating where I've placed these foot points. They're called foot points.
Okay.
So maybe the CME is located right here, but maybe it's a little bit wider. maybe the leading edge is here, but maybe it's actually to the left a little bit. Maybe it's over here. Maybe it's actually farther out. Who knows, right?
Mm-hmm.
And so how is that going to change the model once? So we generate all of these different um, members of the ensemble, and that's what these on the right-hand side, that's what this is. These are all members of the ensemble, and they all have different latitudes, longitudes, velocities, and half widths. And so these are our spaghetti plots essentially. They don't look like spaghetti plots because they're not plotted on a map or anything, right? But
Yeah.
they essentially that's their spaghetti plots, but for a CME. And so we launch 50 of these things. We launched this model
Yeah.
50 times. We don't actually visually observe this model being launched 50 times. We don't see it 50 times, but we get outputs from it being launched 50 times. And so the results allow us to say, okay, maybe there's a larger window of time that this CME is going to arrive. Maybe the KP index, instead of being, when we ran this model just one time, the KP was 5 to 6. But now that we launched it 50 times, maybe it could be the KP could be a 7 or an 8, possibly. Might be lower probability of it happening, but it could happen, right?
Yeah.
So it's trying to get at possible outcomes, even if they're less statistically likely, getting at more outcomes that could happen. And this is kind of this is a histogram, a plot of the velocities from this potential ensemble that I created.
Okay.
And so you see, it kind of looks kind of like a, I don't know, if you're familiar with statistics, it's kind of normal shaped a little bit, a little bell curve shape, that the red line kind of, not so much, but a little bit. And so the point is that there's probably better confidence. There's more members in the middle, so there's better confidence that the velocity of this CME is between this amount and this amount. And it's probably not as likely that the velocity is way over here at 1,000 kilometers per second.
Mm-hmm.
It's probably between 800 and 900 or something like that, right?
Yeah.
So that's kind of the point. But it's important to have the 1,000 kilometer per second member in here, because if that were true, I mean, that could possibly give us a much bigger storm. So
Yeah.
so we try to, it's a little bit like a game of it's like a Rubik's cube. Like, you're trying to, when you create all these members, you're trying to get everything aligned perfectly so that you have high confidence that the velocity is going to be between here and here, and the half width is here and here, and the latitude is here and here. And so, but anyway, the point of doing all of this is to try to get an understanding of, like, is this CME, how certain is this CME going to impact us? Is it going to impact us 100% of the time? Or when those 50 model launches, executions of the model were launched, are only 4 of the 50 going to hit Earth, right? Where, okay, maybe Earth will only be impacted by the CME like 5% of the time or something. So it's probably going to miss.
Makes
So,
sense. I think ensemble is a good way to go because of that, because of the very uncertainty aspect.
yeah, it's a shame that it takes so long to do, right?
Yeah,
There's
yeah.
like there's kind of, it's tedious to essentially put it together.
Mm-hmm.
But and this is the last slide. So just, thinking about the future, trying to get at an understanding of magnetic field orientation, I mean, this is an open problem in space weather that, I don't know, maybe you'll win the Nobel Prize when somebody, I mean, there's work on it, right?
Right,
It's
right.
like people are working on this right now, but it's an extremely important problem. So, that's one way to make these models better. Potentially integrating AI or machine learning, if you kind of support that thing anyway, for making the processes a little bit faster. Just to run an ensemble takes like to run it itself takes 8 to 10 hours.
Right, right.
Um, and to actually create all of the members for it takes like 2 hours or 3 hours. So it's like it's an all day type thing just to answer that question of like, okay, is this gonna impact Earth or not? Um, and then of course, always, Mary Beth, as you had said right at the onset of this, more data, right? Like
Yeah, more
better,
data.
better that's what everyone wants. So better
Yeah.
CME data from other spacecraft would help us um, a lot in terms of the modeling if we are able to use Solar Orbiter and Parker Solar Probe and other um, and it's good now that we have the GOES coronagraph. Of course, we're all very excited about that in
Yeah.
the operational community to be able to have something that is going to be running 24/7 now. So,
Yeah, that is nice.
yeah, it is very nice. We're looking forward to actually like being able to put that in our measuring tools, that data. So,
Sweet.
yeah. Yeah. And so that's it. I just wanted to say thank you so much for everyone's attention, and I really do appreciate you having me on to chat about this
Yeah,
stuff.
this was great because like even it's nice to go through this entire model like that, like break it down from, you know, because honestly, even though as much as I've been working with this stuff, I didn't really realize that in that the little circle in the middle there actually is at that 21 AU,
Yeah.
and that the sun's
Yeah.
inside that. So, I pick up some stuff every time. So it's cool.
Yeah, yeah, there is some good stuff inherent in this model.
Yeah.
There's some other, let's see if I can grab it here. Um, yeah, this red and blue indicate kind of the different polarities as well.
Okay.
Um,
Yep.
and there are two white lines, solid white lines, of course, that are denoting the IMF polarity. So you would
Mm-hmm.
be able to determine a solar sector boundary. We're
Aha.
getting a little into the technical weeds
Yep.
so my apologies to folks, but yeah, you could potentially determine like a solar sector boundary using this model with this white line when that white line were to cross the sun. So one side of this is going to be like, yeah, it's actually this outer color here, which is blue.
Mm-hmm.
So this sector is like the negative sector, and then this red sector and I can't shade it or anything, but yeah,
I could see it.
yeah, yeah. So and then there's some just kind of like field lines that are kind of red, black and white here that are just kind of there essentially. But
Okay.
yeah, there's some interesting nuances and stuff to
Yeah.
this, and um,
Well, everybody in the chat says thank you for the presentation. Is really
oh yeah,
good.
yeah, my pleasure. I probably should have yeah, I feel free to direct message me. I do run the Space Weather Watch channel. It's just kind of an educational type, social media handle.
Yeah.
I should have said that at the very very beginning, but
It's all
um
right. It's all
yeah,
right. Yeah.
I love chatting with people all the time and love messages and stuff. So I always love talking about
Yeah.
space weather with people. It gets me very excited.
Yeah.
So
Because it is. It's cool. And then I do have to say, so Todd wants to give you a shout out. He,
oh, tell him I say hello. I'd love to talk.
yeah. So,
He can hear me.
yeah. So, hello.
He can hear me.
Because he's,
Yeah.
I've been trying to like sort of monitor the chat, but it's kind of, it's hard, when you're paying attention to this and that. But yeah, everybody says this was great. So yeah, thank you so
Yeah,
much.
no, thank you so much for having me on. I've been watching all of the other folks that have been on, and
Yeah.
like, yeah, I always learn something new every day from like the colleagues that I've worked with
Uh
for a
huh.
few years, it's like, oh wow, that's really how it is, like,
You're
like
right.
you pick up little things
Yeah,
all the time.
little
So
tidbits all the time, and that's how you
yeah.
start learning more and more as it goes on, and yeah. So
Yeah, yeah. I'm hoping to be able to. I know that you all have like an Aurora. I don't know if is it Aurora Photography Summit or a Chasing Summit or something like that. I mean, I definitely need to be more involved with kind of the community that's out there, right? Like,
yeah, I mean, there's groups, there's Facebook groups, and then what you're that's the Aurora Summit, and it's in
okay.
Wisconsin every year.
Oh,
So
that's
it's in
neat.
Melissa Kalen runs that. If you look her up,
Okay.
and
Sure.
Dixie Burbank. So those two kind of spearhead it,
Hmm.
and it's kind of a neat little thing. It's an annual gathering of
Hmm.
different people, and they do it. They have it's a wide variety of stuff. You know, it's like even from photography to cultural stuff to the science. So it's kind of like
Yeah,
very
yeah.
varied in topics, which
Hmm.
makes it interesting. Um,
Multifaceted.
yeah.
That's
So
cool.
the sciencey topics tend to be pretty popular, even if it's above
Mm.
most people's comprehension at the time.
Hmm.
But it kind of it instills that little nugget of like, hey, I want to learn more about this.
Exactly.
Yeah.
That's the curiosity, right?
Mm-hmm.
Aspect of it is
Yeah.
like that's how I kind of got into this was like, huh, I don't know what that means, but now I'm gonna go look it up,
Yeah.
you know? Like just
Exactly.
continuously asking questions is like it, yeah.
That's what I do every day.
Yep, me too.
Like,
Me too.
like, why is this happening now? Like, like we were talking, me and Tanya were talking about, she's, helping me with this magnetosphere presentation that I had to do over the weekend. And it's just the stuff we've picked up in the past year with how the magnetosphere functions is both, it's really awesome, but it's like kind of overwhelming at times too because there's
Yeah.
just so much to that, and there's a lot that
Hmm.
we don't even really understand completely.
Yeah,
So,
there's so many nuances to that. The previous director for our team, her background and expertise is in magnetospheric physics,
uh huh,
and my goodness, I mean,
yeah, it's
like,
just
yeah, she when she's talked about stuff she was passionate about, I was like, whoa, this is way over my head. But
yeah,
there's so many,
it's funny because like yeah, just like us talking, they're all super passionate about it. I'm like I
yeah,
don't know
yeah,
anything that you're talking about, but it sounds cool, and I'll read some papers and try to
uh-huh.
understand it.
That's all you can do. Exactly.
Yeah.
That's
Well,
funny.
let's see. I'm gonna do one more skim. I think
Sure.
we ended up getting all the questions in though,
Awesome.
unless Tanya saw any that I missed. Um, yeah,
There is a question
yeah.
about the green dots that you were
Oh yeah,
showing
yeah.
for
Sure.
the ensemble modeling.
Hmm.
So what are they and how are you putting them on?
Great question. Yeah. I'm gonna reshare.
Yep, go for it.
And let's see.
It's like maybe.
Is that sharing or no?
No, yeah. You'll have to try it
Ah,
again.
okay.
Like I know I didn't turn it off. There we go.
Oh yes, I need to hit the share button, of course.
It's all good.
That's funny. Okay. So this is a tool. Actually, this tool is it is available to the public in that it is a publicly facing website called StereoCat. And so this was a tool. I believe it was is developed by well, it's developed by CCMC, but there was an intern, I believe. I want to say mid 2010s or something like
Mm-hmm.
that. And so the idea of using StereoCat is to um, quickly and easily be able to create ensemble members. And what it does is match foot points. So it will take this foot point, right, and match it. So it's combinations, right, like combinatorics, where you have this foot point matching with this foot point and matching with this one. So that's one type or one member. But then you have the same foot point, but now you're matching it with two and two. And so it's a way to quickly be able to um, essentially create a lot of members from just a handful of actual measurements. So the beautiful thing is I'm not actually measuring the CME like 50 times. I
Mm-hmm.
can measure it maybe 7 times and create 49 members.
Okay.
What are they? They are essentially this is a before and after image. The left side, both of these left sides here are a before image, and the right sides are the after image. Um, this is a coronagraph where you can actually see the CME coming out and propagating outward. And so this foot point describes where the CME is able to be seen. This middle dot is the leading edge of the CME. And then the left and right most dots, they kind of constrain the half width of how wide the CME is. And so this particular demonstration that I did here was, I think, more for entertainment purposes only.
Mm-hmm.
One of the limitations, right, of this particular model is it doesn't handle these very not model, but this measuring software is that it doesn't for these really wide events, it doesn't really handle those very well. But in essence, the the circles are showing where I placed the foot points in previous measurements. So you can see that I'm pretty confident right here where my mouse is pointing. I'm pretty confident that the leftmost portion of the CME is like, it's pretty close. Like I have them all pretty closely,
Mm-hmm.
um, you know, in space. I have them pretty closely aligned. But on the right side, look at that. Maybe it's a bit. So this is indicating that I don't really know how wide this thing is on the right-hand side,
Okay.
right? So this is
Yep.
indicating some sort of uncertainty. And the middle here, you can see there's a lot of different leading edges, right? The leading edge could be on the left side over here, but maybe it's on the center, maybe it's on the right-hand side. Who knows? Who's to say? Um, and what these do, by having the different measurements, they actually create um, latitudes and longitudes that are different by a few degrees. And that makes a gigantic difference when you're plugging it into that model, right? It's like if the longitude is 5 and the longitude is 10 and you launch the simulation, there is going to be a slight difference of the impact at Earth because now the impact is going to be on an angle. It's not going to be direct, right?
Mm-hmm.
So, so that's kind of the point. These are foot points that are used to try and determine the uncertainty of
Okay.
the. Yeah, hopefully that was helpful.
I Yeah, I think so. We'll see if there was a rebuttal in the chat, but so far so good. And then
And another question is
yeah.
basically, what is your take on AI solar wind modeling? Any anything promising in the pipeline, or it's going to be a big challenge?
Interesting. I don't know how much I can actually speak to that on like my knowledge bank of like AI models that are running solar wind. Um, I think that the AI for the ambient solar wind, I think that there would probably be more successes than the cone model, which
Mm-hmm.
requires a CME. Um, the and I can talk to that. My personal opinion is that um, it might be a very, very long time before um, AI is able to train up properly on measuring a CME, particularly these really faint ones that are almost indetectable. It requires, so to speak, a human eye to be able to see the CME. So I think there will be like strong difficulties with AI trying to measure CMEs, and there are some folks that are working on AI measurement of CMEs, but the data sets, right, that they use are typically limited to these very beautiful, bright events, and also having a knowledge of like where that eruption occurred from, the latitude, right? They're
Yeah.
like a little bit of bias, right? They kind of know where the latitude and longitude is already. Um, but sometimes we get a CME and we will actually spend like all of 40 minutes looking to see was this on the Earth facing side of the sun where it could be in this direction or was it behind, right? We'd have to like almost by process of elimination almost because there's no observation, there's limited observations back there behind the sun. So um, by process of elimination, it could be behind the sun, right? And
Mm-hmm.
so the beautiful thing about space weather forecasting is it does require like intuition, which that's not something that AI can handle right now very well. Not yet.
Right.
Maybe in the future.
Yeah.
But there's some complex linkages that need to happen first. That I could imagine I could imagine, right, a case where you have a really minor eruption on the Earth-facing disk, and you get at simultaneously you get a really big bright CME, right?
Uh-huh.
In maybe a similar direction. And only a human being would be able to say, okay, based on what I'm seeing here with my eyes, this is probably not on the front side. I know I see an eruption, but it doesn't really make sense, right?
Right,
Like
yeah.
it doesn't correspond with this really powerful CME, right? That is probably behind on the other side.
Yeah,
Um,
I think
so
there's been several instances just in the past year of this very thing you're talking about, where like you have to, the forecasters and even us, the Twitter forecasters, have
uh-huh.
had to like go through and basically, like you said, process of elimination. Like,
Yeah,
was this on the front or the back? Because
yeah,
yeah.
right, right.
So,
Yeah. And I mean, there's some successes.
hmm
With the ambient solar wind, possibly, yeah, that could be a good use case for launching a model there. Yeah.
yeah,
Um, but
yeah. Sarah
so
Sarah said
that's
that she would be concerned with the AI due to every structure and every event being different. And
yeah.
yeah.
Yep. Exactly.
hmm
Exactly. A great point, Sarah. Yeah. Every one of these events is sort of has its own quote unquote fingerprint, right? Um, that's the fun thing about being a space weather quote unquote forecaster or working in space weather operations is like you walk into work, you have no idea what you're going to see there the next
Right.
day, right? Like it's like sometimes you get these three-headed solar storms and you just have and it's like you're going to spend the rest of your day trying to figure that out. And piece it together. It's like it's a puzzle, so to speak.
Yeah.
But and you can't train on that. I mean, it's. I mean, you can, but everything is going to have to be boiled down, and yeah, all these there's all these complex cases where um, AI is going to have difficulties for sure. So anyway, if anyone is interested in doing space weather, I'm trying to make the point that I think you're safe.
Yeah. You're
I think
safe.
you're safe
Safe from
for
the
the
AI.
time being. We'll see.
At least one industry is safe for now.
Yes, at least yeah, exactly right. At least one.
Oh,
That's
that's
funny.
great.
That's
All
funny.
right, Tanya,
All right.
did we cover all the questions, I think? I know you guys are having a really fun conversation about neutrons and aurora.
Yes, we are trying to figure out we were trying to figure out if neutrons can actually drive aurora because um, they're definitely flowing from the sun. We think about
Yeah.
plasma as just basically ionized gas, but I'm sure there's some neutrals in there. Um, but it's kind of hard to accelerate neutrals with magnetic field.
Mm,
And that's how
hmm.
aurora works. So
Right.
those
hmm
magnetic reconnections and where particles slow that ultimately create aurora, it's not something that's going to work on neutrons or any type of neutral particle. So I don't see how neutrons will participate in aurora. Neutrons are generated by a very different process too. So
Hmm.
you could see neutrons as a sort of side effect of galactic cosmic rays.
Hmm.
I'm a physician, so for me, everything is a side effect. And
Everything's a side effect.
it's a byproduct. It's a byproduct. It's a sort of
That's funny.
cosmic rays generate sh particle showers when they finally get to the Earth's atmosphere, and neutrons are part of it. So we get tons of neutrons from galactic cosmic, not tons, but we have a fair amount.
Yeah.
Hmm.
And there are some
Hmm.
events, even some of the solar events that Chris, you probably could talk about when we
hmm
do have ground level enhancement
Mm.
and a lot of neutrons, but they're not sort of there by themselves. They're coming from typically from high energy protons. And we get some shielding when we get CMEs. They're like magnetic
Yeah.
bubbles, and
Yeah.
they're
Yeah.
extra shield
Yeah.
where we see drop in neutrons. It's fun to monitor. It's sort of
Yes.
another way for us to tell that CME is somewhere nearby, but
Yeah.
Yes.
forecasted
Yes.
to arrive, and it's close, but it's really not affecting Earth. It's
Hmm.
affecting Earth by shielding, but we're not seeing the magnetic effects of it. So kind of sad. We can wave it goodbye.
Yeah, no,
Like,
there was a I think like maybe 4 or 5 months after after I started with NASA, there was this really interesting event where we had a I I don't know if the month is correct, but in any case, we had a really strong X-class flare on the western limb,
Mm-hmm.
and for whatever reason, we didn't really see particles from it. The radio signatures were kind of
Ah,
indicating like, oh yeah, there might, there was particle release with this flare and everything. So we got radio data, but we didn't really see much in terms of the particles. And then we had a CME arrival the next day. And when the CME arrival occurred, the particles then shot up. And that was like, for me, that was like, wow, that was really, really insightful for me to understand like, oh, there's much more complex things going on here that, like you said, Tanya,
Mm-hmm.
the solar storms can literally be they're magnetic clouds, so they're able to actually serve as like shields. So, yeah, it's very that event will always stick with me. I don't remember the exact day, but um, just the fact that I was kind of new as well and
Uh-huh.
still kind of getting my bearings, like I don't know, very that'll stick with me for
Yeah,
a long
because
time.
it's like
yeah,
it's a
we had
memorable
a
thing.
similar event. Yeah, we had a similar event not that long ago when there was eruption on East Limb, and there was sort
Mm,
of expectation that we're going to see some particles coming from that
hmm
because it was a fairly strong flare.
hmm
And it didn't happen for a while until the shock of CME arrived.
Yeah,
And
yeah,
then protons actually went up. So,
yeah.
yeah,
Very interesting.
definitely can happen.
Mm, very
Kind of
interesting.
fun.
Yeah,
Not.
that's cool. Mm,
Well, sweet. Well, I guess on that note, we can um end it, I suppose.
sure.
I don't see any,
Thank you
I
so
don't
much
see any more questions, so.
thank you so much for having me on this evening. I will be looking forward to the next speaker and
Yeah.
just if you all just have maybe I don't know, maybe we could do like some just general chatting and just have a whole bunch of folks on maybe
Yeah,
if it's
we've been talking about that, like just getting like
yeah.
a bunch of you guys together and just having like an open discussion or what on
Yeah.
whatever.
That
And
would be fun.
I
That
think it
would be
would be a
fun.
ton of fun. So,
Yeah.
we're
I
definitely thinking
agree.
about it.
I agree.
We
That's
need a
good.
big event. We need a big
Yeah.
Yeah.
event to
Yeah, maybe
analyze.
that's what it is. We don't
That would be fun.
we just don't
Yeah.
have anything super big to talk about. Like
Mm.
May of last year. That
I
would have
was
been
gonna
a
say May is right around the corner. We'll
yeah,
see.
so
See.
maybe
Yeah. We'll see.
But really no, thank you so much for being
Thank
here.
you.
This was
No, thank you for having me.
super
It's an
insightful.
absolute pleasure. It's a pleasure. And it was so nice meeting both of you too.
Yeah, likewise. And then
Thank you. Likewise.
everybody in the chat, said thank you again. So yeah,
Awesome.
it was all well
Awesome.
received and appreciated.
Good.
So
I'm so glad. Lovely. Anybody can message me. I'm always available. So, yeah.
fantastic. All right, well, everybody have a great night, and then we'll be
Thank
back
you so
next week
much.
with something. So.
Awesome. Awesome.